Should I keep going?
Yeah, we muted her, sorry.
No worries. So I want to thank the association again for allowing me to participate in the preparation of America's next generation of physicians. I'm going to go ahead and ask if I can go ahead and share my screen. Is that okay, Lauren?
Yes.
Okay, thank you.
You were able to do that.
Awesome, awesome. This is the new normal.
Yes.
So can everybody see a slide and another screen?
Yes, I can.
Yes.
Okay, great.
We got everyone on mute, so just let me know.
Okay.
I guess if you have any questions, put it in the chat and we'll answer them.
I think that so you can see me and you can see a slide deck right now, correct?
Mm-hmm.
Correct.
Okay, great, thank you. So I think that what we're gonna be doing today is with the low-tech setup that I have, you're gonna see me coming in and out of the screen because I have to advance, go to my computer to advance to the next slide. But other than that, I think we should be okay. And also, thank you, Lauren, for muting everyone for right now. At various points, I'll ask you to unmute so I can take questions. So let's go ahead and get started. So thanks again to the association for allowing me to participate in this MCAT physics test prep. I'm Rodney Green, the president of Prep Plus. The email address is there on the first slide, prepplusinc@gmail.com. And so let's go ahead and get started. So once again, this is an MCAT physics test prep. The outline for today is indicated there. I'll give an overview of the physics section of the MCAT, of the structure of the overview of the an overview of the structure of the physics questions on the MCAT. A slide on different strategies. I'm sure you've heard about different strategies for taking standardized tests, but I'll go ahead and give you some strategies today. And there are two types of physics problems on the MCAT. There's so-called freestanding problems and passage problems. And we're going to spend the lion's share today working through some example freestanding and passage problems today. And so today, again, I'm excited to participate in the mission of the association. Mentees will be able to get a 10% discount for online tutoring from me with the secret code EMI2020. Emmy is my cat's name, and you can see a picture of her there. She very graciously allowed me to boldly put her name to promote this online tutoring. So there you go. So you have until July 31st to use that 10% discount with the code EMI2020. So first of all, who am I? I'm Rodney Green. I'm the president of Prep Plus. I've got plenty of papers from lots of institutions indicated there. Most recently, a PhD in physics from the University of Illinois. Actually, it wasn't that recent. It was quite a while ago. And a very long time ago, I was a captain in the US Air Force. After I got my PhD, I was a tenure track assistant professor at Wayne State University in Detroit, Michigan. I taught the largest physics class in the department at the time. It was a class full of pre-med students like yourself. After I left academia, I got into investment banking, where I've been for the last 20 years as a quantitative research analyst, developing models for pricing securities for a number of investment banks. Recently, I decided I needed a timeout from the investment banking grind and took a step away, and I'm returning to my roots of teaching, and so I formed Prep Plus, this online tutoring firm. And again, you can email me at prepplusinc@gmail.com to purchase additional sessions with me. So let's go ahead and get started. So first of all, an overview of the structure of the MCAT. There are 4 sections to the MCAT. we're going to focus on a piece of the top part, and that is called Chemical and Physical Foundations of Biological Systems. So that has 59 questions over 95 minutes. So that gives you about 1.5 minutes per question. So, so that's what we're going to focus on today, is that chemical and biological foundations of biological systems. Now, that section of the MCAT has about 15 physics questions on it. So that's really the focus of today, is those 15 questions in that section of the MCAT. So 15 of those 59 questions are going to be physics-centric questions. And of those 15 questions, there are two types. There's passage-based questions, and there are standalone questions. And a standalone question is sort of your typical question that you probably saw as in your physics class as an undergrad. It's a statement with 1, 2, 3, or 4 sentences, and then you have 4 or 5 multiple choices, and then you go, and then you're done. You go to the next question. A passage-based question is a much longer narrative, and then there may be 4 or 5 multiple choice questions after that. So in the entire chemical and biological foundations of systems, of biological systems section, there are about 44 passage-based questions and 15 freestanding questions. So that's for the whole section, but the physics section is only 15 questions, and it's a mixture of passage questions and freestanding questions. So again, you've only got 1.5 minutes to do an individual question. For the passage-based questions, let me go to the next slide. So this is about strategies for the passage-based questions. It depends on how many questions are on there, but you have about 7.5 minutes to read the passage and answer all the following questions. And then again, for the freestanding questions, you have about 1.5 minutes to read it and answer it. So I've got some strategies that you may find useful, and of course you're free to customize them as you see fit. I want to focus again on the right-hand side of that table. For the freestanding questions, you know, you have a choice. The MCAT is web-based. You're going to be sitting in front of a computer and you're going to be working on it. And you can make annotations, you can underline, you can make notes to self on it, and then you indicate your questions. I suggest, and you always, I believe you have the choice of either answering a question when you see it or skipping it and moving on and then coming back to it. I suggest that as you encounter these freestanding questions, you go ahead and do it. If you just don't know the answer, if you don't know if it doesn't come to you, then you can make a note and then come back to it later. But if at all possible, I suggest that as you come upon these freestanding questions, you go ahead and answer it. And again, you only have 1.5 minutes. And then if you're getting toward the end of time, then you can go ahead and guess. You're not penalized. You know, I never really understood what they meant when people said you're not penalized for guessing, but that's the official position of the MCAT organization. You're not penalized for guessing. So every question should have an answer on it. Even if you're making a wild guess and you're running out of time, just go ahead and fill in the dot. And then if we look at the left-hand side of that table for your passage-based questions, read the first 1 or 2 sentences and make an assessment. Is this something I want to do now, or do I want to save it for later? If it's something you want to do now, then proceed with doing what I call mapping the passage. If it's something that you don't want to handle it right there on the spot, make a note to self, flag it to return to that question and move on. So try in the interest of time, try to make a quick determination if you want to answer the question right then and there, or move on. Getting a little bit of feedback if someone could please mute their mic. Then if you decide to go ahead and work on the problem, then I suggest you map the passage. And at the bottom of the slide, I give you some bullets on what I mean by mapping the passage. I mean, highlight key pieces of information so that your vision and your concentration really zero in on those things that you highlight, such as constants, numbers, dimensions, key terms, and if necessary, draw a little diagram and label the things on the diagram. For example, if it's a force problem, I suggest you go ahead and draw yourself a free body diagram and draw the force vectors on it, because more than likely you'll need the information on the diagram to answer the question. And I'll have an example of what I mean by passage mapping with some of the examples. And don't worry, at some point I'll take a break for questions. I just wanted to get through these initial slides right away. So I just want to do a very surface, high-level review. You know, I don't know what's going to be on the MCAT. They always change it every time. But a typical, in my physics career, education career, pulleys are very standard sort of kinematics or classical mechanics question. And so I've got a little slide in here about reviewing concepts for pulleys. So let's just take a minute or two to go over this real quick. So with pulleys, the first thing, of course, that you want to do, as with any kinematics problem, is draw a free body diagram. So here we have a pulley attached to the ceiling, and you have a mass attached to one side of the rope, and you're pulling down on the other. So the force down is tension, and it goes along the entire rope. So you have a tension force along the entire rope.
I'm about to roll this out to the garage.
If you're interested in figuring out what's happening to the attached mass, you draw a free body diagram. The dot, it represents the center of mass. The center of mass is the sort of the imaginary point where all the forces act. So you have a mass, which may be a box, it may be a car or whatever. It has some volume, but we will represent forces acting across that entire volume as a single dot, which is the center of mass. And in this example, we have the force of gravity going down, that's mass times the acceleration due to gravity, and the tension in the rope pulling up on this mass. Vectors provide magnitude and direction information. So typically in a problem, you'll have to write a vector equation for both the horizontal direction, the x-axis direction, as well as the vertical direction or the y direction. So vectors, it's very important to remember that vectors provide both magnitude and direction information. And you can write a vector either with boldface or with an arrow on top of it. And in this type of problem where gravity is acting, you have acceleration due to gravity on a particular celestial body. So some questions talk about something going on Earth, and some questions talk about something going on the moon or Mars or Pluto or some other celestial body. Make sure that the acceleration due to gravity that you use is for the celestial body cited in the problem. So if it's Earth, the acceleration due to gravity is 9.8 meters per second squared. and that's approximately 10 meters per second squared. And then the cool thing about pulleys is remember that the force of tension goes throughout the entire rope. So here we have two pulleys. One is fixed to the ceiling, and another one can move up and down as you pull.
Emma, could you do me the biggest favor, bro?
Dr. Loeb, can you hear me?
We can hear you now. You went out for a while.
Okay, great. Thank you very much.
Got you back in.
Okay, no worries. Don't worry, I'm going to be getting to the good stuff in just a second. The point that I wanted to make in this pulleys review is that the force of tension goes throughout the entire rope. And so if you draw a free body diagram, you're going to focus on this pulley. And so there's the center of mass for this pulley. There's the force of gravity going down due to this mass. Now, technically, in a physical problem, this pulley would also have a mass. I can bet you 99% of the time, the question is going to say that all the pulleys are massless. So you don't have to worry about force due to gravity due to the individual pulleys. So, you know, I'm not going to guarantee it. They're going to say the pulleys are massless, but usually they do. And so for this pulley, there's a force due to gravity due to the attached mass, and that's mass times acceleration due to gravity. And then you have these two ropes attached to this pulley, and they both have tension. They both have the force due to tension, and they're pointed up. So that's the cool thing about these pulley problems is usually you have one place where you're pulling on it, but then the actual action of the force sort of gets multiplied. And you see that after you draw the free body diagram. There's no magic going on. There's no secret ghost hand holding these things up. Everything, all the forces are represented by force vectors. And so once you draw your free body diagram, you draw your, that the net forces is equal to, you add up all the forces and make sure you keep the signs plus or minus to represent whether it's going up or down. And the total net force is equal to mass times acceleration. So typically these kinematics problems will ask you, what is the acceleration of something if you apply some forces to it? So I'm going to go ahead and move on to the first problem. And I'll go ahead and take questions after I go through the solution of this problem. So we see, so, you know, nobody likes to have people read stuff to them, but I'm going to ignore that and go ahead and read this stuff to you. And then I'll go to my board and work this out. So for this freestanding problem, you have four frictionless, so there you have frictionless, massless pulleys arranged as shown below. If you have enough force to lift a 40-kilogram object without any pulleys, what is the maximum mass of the couch that can be raised with the pulley system? So we look at this picture and we have 1, 2, 3, 4 pulleys. The couch is attached to a couple of these pulleys. I'm going to be pulling down on this rope with enough force to pick up a 40-kilogram object. And so if we're lucky, so the question asks us to figure out what's the maximum mass of the couch. that can be picked up. I forgot to mention that I will be distributing these slides to Lauren, and she has graciously agreed to distribute them to everyone on the call. So I'll send her a PDF with all the slides with the solutions to Lauren, and she can distribute them. So you can just sort of listen and look, and you'll get the details in a PDF after this talk. So the first step, so that's the problem. This is a freestanding problem, and recall, I suggest that as you see these freestanding problems, you go ahead and work on it. So the first thing you want to do is draw a picture. Unfortunately, I'm tall and my tripod is not. So the first thing you want to do on this, usually on these kinematics problems, is draw a picture, draw what's called a free body diagram. So we're going to draw a free body diagram about the couch, on the forces on the couch. So the couch we represent as a dot, which is the center of mass. All of the forces on the couch act as though they're working on a dot, the center of mass. And so that the thing about this is you have the couch is attached. There are 2 attachment points on the couch for the rope. And you got 4 pulleys going on in this picture. Don't let that confuse you. The couch is represented by a dot, and all the forces acting on that couch are centered on, or act as though they only act on a single dot. So the couch, of course, has a force down due to gravity. So the mass of the couch times the force due to gravity of Earth. You know, they haven't said otherwise, so we believe this is something on Earth. And so something is pulling up on the couch, and it is the force due to tension. And we have 1, 2, 3, 4 ropes that can pull, that can apply tension up on this couch. So I'm just going to, so that's 4 times force due to tension. Okay, so that's my free body diagram. Gravity going down, the mass of the couch. So let's write this. Gravity going down on the couch, and then the tension of the ropes pulling up on the couch. That's it. No other funny business. So now let's write Newton's law, which is that the net forces, we write down the net forces and set that equal to mass times acceleration. So the net forces, well, we have this guy going up, 4 tension forces going up, and we have gravity going down. And that the net forces are equal to M times A. And here, M is the mass of the couch. So the problem gives us some values. We're going to plug those values in. So 4 times the, sorry, I have a typo here. It says that you have enough force to lift a 40-kilogram object. So the weight, the force due to gravity of that 40-kilogram object is its mass times the acceleration due to gravity. So that's 40 kilograms times approximately 10 meters per second squared.
Rodney, we have a question in the chat from Sabrina. It says, so for the tension forces, it doesn't matter how many points are actually touching the couch, but instead how many total tension there are?
That is correct. All the forces, when you draw the free body diagram. The couch is a three-dimensional object. And in this problem, there are two attachment points on the couch for the rope. But at each attachment point, there are effectively two tensions pulling up on the couch. Don't get freaked out by attachment points being all over the place. The only thing that matters is how many tensions are pulling up on it. And in this problem, there's 4 of them. There's 4, 1, 2, 3, 4 ropes pulling up on this couch. All of those forces, even though they're all over the place, act as though they're acting on a single point, the center of mass of the couch. So the couch collapses into one dot, and all the forces act on that one dot. You got 4 tensions pulling up, 4 tensions pulling up, and then you have gravity pulling down. So thank you very much for that question. So we draw our free body diagram, and remember, vectors have a magnitude and a direction. So here we only have a vertical direction. So we're going to write our Newton's law equation just for the vertical direction. 4 tension forces going up, force due to gravity going down, and that equals mass times the acceleration in the vertical direction. So this is an equation that only has to do with motion up and down. And so now they've given us some values in the problem, so I'm just going to plug those in. 4, the maximum mass that the problem says you can handle is 40 kilograms. And then the weight of the associated weight or mass or force due to gravity of a 40 kilogram object is its mass times the acceleration due to gravity. So so this is the force due to, this is 4 times the force due to tension, and then gravity minus m times 10 meters per second squared. So if you plug all this stuff in, you will get, I believe I have a typo on here, but it is going to be 200 kilograms. So one of the choices on the problem, I'm going to have to fix this typo before I send this to Lauren. But one of the so you'll have 4 or 5 choices on this freestanding problem. One of them will be for the mass. So once you get this, you just apply algebra to solve for the mass, the maximum mass of the couch that you can handle. So are there any questions right now?
I just want to jump in and mention that for those who joined the call late, that there are some pieces that Dr. Rodney Green recommended that you know prior to going into the test. So one is the force equals mass times acceleration. That's a general physics equation that everyone should know. Force equals mass times acceleration. And then he also did give us the acceleration due to gravity, which is 10 meters per second squared. So that's a given. And he recommended that you know that going into the test. So that's where those numbers and those equations came from. So I just want to make sure that everyone takes away those points.
Thank you very much. So in the interest of time, I'm going to go ahead and move on to the next slide. Now I've got way more slides than I'm going to be able to cover today. And that that's a good thing, because you'll have a lot of stuff. Once you get the PDF for this presentation, you'll have a lot of problems with a lot of solutions that you can go through. So let me go ahead and move on to the next slide. So again, friction is a typical area that is covered on a physics test for the MCAT, and it's usually boxes or something on an incline, and what do you have to do? So let me just quickly go over some key facts about friction. So the force due to friction is some coefficient of friction times what's called the normal force. And you have what's called a force due to static friction and a force due to kinematic friction. So what all that is talking about is if you have, let's say this is a tabletop, my hand is a tabletop, and you have an object on the tabletop, and I want to push it. So I'm pushing on this thing, and for a while it's not moving. The normal force is the force of the tabletop that's holding it. So you have, otherwise it's just in space, but it's sitting on a tabletop. Its weight is going down. The tabletop is pushing up on it. So this is the normal force, the force of the tabletop. And the force of the tabletop in this example, it's exactly counteracting the force of gravity that's pulling it down. So the normal force actually is the weight of this object. So it's on the tabletop and I push it and it's not moving. It's not moving. It's not moving. It's not moving because there's a force of friction that's going in the opposite direction. That's that's counteracting the force that I'm applying. And that is called, so this thing is not moving, so that is called, so the relevant coefficient of friction is the coefficient of static friction. This thing is not moving. So I'm going to keep pushing, then all of a sudden it's going to start moving. But there's still friction going on. And the friction that is applicable is kinematic or dynamic friction. And that has a different coefficient of friction. It's the coefficient of dynamic friction. So once this thing starts moving, you use the coefficient of dynamic friction. If it's still stationary and not moving, I'm not pushing it hard enough, you use the coefficient of static friction. It's the same law. It's a normal force. The force due to friction is the normal force times a coefficient of friction. It's just a question of whether you use static coefficient of friction or the dynamic coefficient of friction. So usually a lot of these problems talk about there are things on an incline, and in order to decompose the problem into an X direction and a Y direction, you have to use the sine and cosine function. Don't get freaked out about sines and cosines and trigonometric functions. I've got the definition of them up here. And the nice thing about them is you can use sines and cosines to break this force up into X and Y coordinates. So in this example, you have a box, you have a mass. It's on an inclined plane. The inclined plane has an angle of theta degrees. So if I'm pushing on it, and I don't indicate that on this diagram, I'm pushing up on this box, there's going to be a force of and unfortunately I've got another typo here. If I'm pushing up on this box right here, pushing up on it from low to high, there's going to be a force of friction in the opposite direction. And so this arrow should be in the opposite direction, a force of friction that's going down and against it. And so this box is going to be stationary, stationary, stationary as I'm pushing on it. And then eventually it's going to start moving, and that is kinetic friction or dynamic friction. So I would use the coefficient of kinetic friction to describe the force due to friction. And then we can use the sines and cosines to decompose these forces in directions along the incline and perpendicular to the incline. And I think I have an example on the next slide. So, and fortunately I have the correct arrows here. So on this example, it's another freestanding problem. We have a box of mass M sitting on an incline of theta degrees, and it requires an applied force F up along the incline to get the box to begin to move. What is the maximum coefficient of static friction? Okay, so I'm gonna, unfortunately, because in the interest of time, I'm going to have to kind of go through this kind of fast, and I regret I won't be able to take any questions because I want to get to mapping a passage question. So let me just go through this one kind of quickly. I apologize for that. So, you know, the first thing, as I said a few slides ago, with these force questions, oftentimes the first thing you want to do is draw a picture. And the picture you want to draw is a free body diagram. So we're going to focus on that box. All the forces acting on that box act as though they're acting on a dot, which is the center of mass of the box. So here's our dot. And we have the force of gravity that's going down. They haven't said otherwise, so we assume this is Earth. The relevant celestial body is Earth, so the force of gravity is going down, and it has a value of 10 meters per second squared, or the acceleration due to gravity is 10 meters per second squared. So this is the mass of the box times g. We have the problem says I'm pushing up on it with that force. And the question says we also have some friction acting on the box. So friction, if I'm pushing up on it with this, friction is going to be operating in the opposite direction. So I'm going to draw friction like that. That's my friction vector. And we know that, you know, that we're not quite done. Friction depends on a normal force, okay? So we're on this incline, so normal means perpendicular. So the normal force acts perpendicular to this surface. This surface is the incline. So the force, the force due to friction is proportional to the normal force, which is perpendicular to the surface. So we're going to have to figure out what the normal force is. So we're going to draw the normal force. So this is F normal. So this is the raw free body diagram of this for this problem. So now I said you need to decompose this, these force vectors in a direction along the incline and perpendicular to the incline. Now we're mainly interested in what's happening along the incline because this force, this external force acts along the incline. So now we have to break up all these force vectors into a direction along the incline that we're mainly interested in and perpendicular to the incline. And that's where we use these trigonometric functions. And I'm just going to write down the result. So that one. So this is mg sine theta, mg cosine theta. Okay. So now we have broken up the force due to gravity in a direction that's along the incline and perpendicular to the incline. So now we can go ahead and solve this problem. So the question talks about the force F is applied along the incline. Okay, so let's write a force vector along the incline, a force equation. So the force along the incline is the external force that's applied. It's called F. That's from the statement of the problem. Minus this guy, it's going in the opposite direction. And there's also this force due to friction. So that's all that's going. Those are the forces that are acting along the incline. You have this force due to gravity going down the incline, and you also have the force due to friction also going down the incline. So we have minus mg sine theta. And if I move my enormous head, mu static mg cosine theta. So now this is Newton's law along the incline. And then the problem asks us to solve for the static coefficient of friction. You can go through the algebra to solve for this, and the answer is going to be in terms of all this stuff in here. Oh, I'm sorry. This is the force along the incline, and because from the statement of the problem, we're talking about a coefficient of static friction. Okay, so static friction means this box is not moving. It's not moving. So this box is at equilibrium. So the force along the incline, the net force is equal mass times acceleration. It's not moving. So mass times acceleration is 0. So all of this equals 0. So then we can solve for the static coefficient of friction, which is what they asked for in the question. So that's just an algebraic manipulation to solve for the coefficient of static friction. And so the question would give you 4 choices. You solve for it, and the correct choice, that's what you indicate on your test. So
I have a question from a student. They're asking, is static tension mg cosine theta, is that one of those formulas that will be given, or is that something that everyone should know as just one of the principles?
Thank you very much for that question. So in order to, I don't really have time to go over it today, but I certainly, since there's a lot of interest in this, in next month's free session, I'll go ahead and go into this some more. But it's really an application of the definitions of these trigonometric functions, cosine theta and sine theta. So I will go over that in more detail next month when we meet. But it's an application of these trigonometric functions. And is that, I would say you would need to know these, because if you know these, I can't guarantee you what kind of questions they're going to give you. So the actual details of how you do this, of how you break down the forces, depends on the actual statement of the problem. But you do need to, I would say memorize these. And then do some practice and practice breaking down forces into the so-called X direction and the Y direction. Practice breaking them up into those directions by using sines and cosines. So I would say you need to know these definitions. Sine theta is the length of the adjacent side over the hypotenuse, and similarly for sine theta. So at this time, I want to, in the interest of time, I want to go ahead and jet through slides to get to a passage problem. Yeah. Okay. So here's a passage problem, and because I have such a scintillating voice, I'm going to read it to you. And then we're going to go over how to map this problem. So students constructed the electrical circuit shown below to study capacitors. A battery with a voltage of 20 volts is connected through a switch to a capacitor and a 100 ohm resistor. The capacitor is constructed from 2 flat metal plates, each with a surface area of 5 times 10 to the minus 4 square meters. The plates are separated by 1 times 10 to the minus 3 meters, and the space between the plates is a vacuum. The connecting wires have no resistance. After the switch is closed and a capacitor is fully charged, a particle with a charge of 1 times 10 to the minus 19 coulombs and a speed of 1 meter per second is injected midway between the capacitor plates. So this is the narrative for this passage problem. And this same narrative will be applied for, say, 4, 5, or 6 questions after this narrative. So you'll have the same narrative and then about, 4, 5, or 6, 7 individual multiple choice questions for this one passage. I would say that most of the problems on the MCAT, whether they're passage problems or freestanding problems, are concept problems. Usually you don't need to use a lot of highly sophisticated mathematics to solve these problems. They're concept problems. So you need to know some equations so that you know what concepts to apply, but I would say you don't need to use a whole bunch of super sophisticated mathematics to work on these problems. You don't need calculus. Algebra is the most amount of math that you will need for these 15 physics questions on the MCAT. So here's the statement of this passage problem. So let's go over how I suggest you map it. So, you read this question. Within the first 1 or 2 sentences, you need to decide whether you're going to work on it or not. And if you decide you're going to work on it, you should map it. So on the interface, you can highlight different things, highlight different terms, and make little annotations to yourself. So I suggest you highlight definitions, constants, dimensions, and key terms. So we're talking about capacitors. Here's a constant, a value, a voltage of 20 volts. Here's another constant, 100 ohm resistor. We have a dimension, surface area of 5 times 10 to the minus 4 square meters. We have another dimension, 1 times 10 to the minus 3 meters. And since we are talking about a capacitor, it's relevant that the space between the plates is a vacuum. So that's a key term. And here's another value, charge of 1 times 10 to the minus 19 coulombs. And here's another value, a speed of 1 meter per second. So when you map the passage, practice this so that you get very comfortable with it. You can quickly go through and really highlight definitions, constants, dimensions, and key terms so that it'll just help you stay focused on what the important things are in this question. And if you should if after you finish mapping it, you decide, look, I don't want to do this question right now, I want to come back to it later, then it'll help you work on the problem if you're running short on time. You just kind of look at those things that you've highlighted and you go through and answer the question. So I wanted to, so that's an example of passage mapping. And then you would go ahead and here is a question, and then you might have three or four more additional questions for this one passage. And I just wanted to kind of go through real quick. Here's another picture of my cat. That's always, when you have a dry presentation, you should always put pictures of animals to maintain interest. This is a talk about physicians. Here's a thermodynamics question with a friendly tip for you future surgeons. Please don't install replacement parts like bones or corneas or orthodontia with a high coefficient of thermal expansion, because if your patient happens to find herself in the Sahara Desert or someplace hot, that replacement part might expand and press against surrounding tissue, and that might cause some distress in your patient. So that's just a friendly tip. So for this particular slide, Emmy was not at all interested. So so that's once again, I've got way more slides than I can go through. I've got all the I'll be distributing these slides with the solutions to Lauren. And if anyone wants one-on-one tutoring with me on math or physics to help you prepare for the MCAT or for the fall semester, please feel free to reach out to me, prepplusinc@gmail.com, and with your discount code ME2020, and you'll get a 10% discount. Thanks again, Dr. Loeb and the association, for allowing me to participate in this test prep session. This is the first of a monthly series. A very special thanks to Lauren for putting this together. It's a real joy to work with you, Lauren. Thank you very much for all your work to get this up and running today. And best of luck to everyone for all the future physicians here in the world. So we definitely need you. So thank you once again. Please stay safe and have a great weekend.
Dr. Loeb-Johnson, are you good?
Yeah, I just wanted to thank the students, and you know what Dr. Rodney Green really highlighted. He's a physicist, so he's trained in this, but what his skill set can do is give you the equations that you should know, the tips, the basic physics key concepts that you should have as you go into the MCAT. So if you have that, a solid background, it can really help boost your score. We want to also thank you, Dr. Green, for coming on with us and for being so generous with your time, and we look forward to future sessions. So that was tough for me too. I was a math major and I had to dig deep. So for the students who kind of felt that the concepts were over their head, that's normal. That's why we're here. We just want to make sure that you get the good information that you need so that you can have a solid performance on your MCAT. So thank you. Thank you everyone for joining, and we hope to see you again next time.